So hopefully you can all see my screen. The idea that I have is I want to give you a short introduction in exposure assessment in occupational epidemiology. And the perspective is that I use the historical developments to illustrate where we have come from, why we have developed particular new concepts, and also at the same time guide you through a little bit of the debates that we had in the past 30 years and the kind of solutions that we have come up with to assess occupational exposure. And I'm used to reading the chat and talking at the same time. So please, if you have any questions, use the chat. I will ask a few questions myself to make it more interactive. So make it also fun for me to teach. Be active. So 3 topics. First, I explain a little bit about the definitions and the methods in relation to study designs. I only touch upon it briefly because that in itself is a complete new course. Then I will spend most of my time on the historical developments to explain to you how we have moved from t-tests in the early 90s to mixed effects models that we are using right now, and that along the way we have developed new descriptive measures for exposure variability. And then the third part of the lecture are actually 2 examples from my own research where I show you how I have used these mixed effects models in studies, one on asbestos and one on bisphenol A. And the examples are an illustration actually of how exposure assessment has developed. But first, some background. I am primarily talking about occupational exposure through inhalation. That is, I think, where most studies are actually doing the exposure assessment. But bear in mind that we can also have occupational exposure through ingestion. We can even have, of course, dermal exposure, and we can have it through injection. Think about needle stick accidents in hospitals. But if you look in literature, then I think the key examples in exposure assessment are on asbestos, solvents, dusts, noise, these kind of classical topics. And then, of course, let's start before going into the actual design considerations. Let's discuss first a little bit about the measurement instruments. So in many occupational EPI studies, we use surveys, either questionnaires that we send out to participants, interviews, sometimes diaries, sometimes walk-through studies that are linked to surveys. We also have expert opinions a lot, and that's linked to the topic of Suzanne Peters, the job exposure matrices. Then, of course, we have the possibility to use registers that sometimes contain hidden information on occupational exposure. And then in the end, of course, we have the possibility to actually do the measurements ourselves. So we measure occupational exposure. We go out to the workplace and we do the measurements. And then we have different possibilities. We can measure in the air, static, in the neighborhood of the worker. We can measure at the worker, so we make it a personal measurement. Or we can do measurements in biological specimens like blood or urine. All these possibilities are there. And in essence, it depends very much on your study design, what kind of choice you will make. And for example, if I were to do a retrospective cohort study, so I'm interested in the effects of a particular agent that is frequently used in companies making a particular product. And I have decided that from 1990 onwards, I have a list of all workers that are being hired by a particular company with that exposure. And I'm sitting at my desk right now, and I'm a PhD student, and I want to do my occupational assessment in this particular retrospective occupational cohort study. And I don't have a time machine. That's the necessary condition here for a good debate. We don't have a time machine, so you have to come up with your occupational exposure assessment strategy right now. Can someone give some considerations how you would approach that? Bear in mind the particular instruments that are on this sheet. Anyone who volunteers to start a discussion, what is an important consideration for choosing particular instruments? Erdem, budget, yes, of course. Can you elaborate a little bit? I think you have to unmute yourself still.
Okay.
Yeah.
Yeah. The budget is important because that's you want to have some how can I say, to some extent you can measure an exposure of workers. So the budget is the most important constraint, I believe.
Yeah, and thinking about budget, for example, you have a particular budget and you are actually able to go out to a factory and do some measurements. What kind of decisions do you want to make?
And also if the measurement will be made at personal level or maybe the environmental measurement, that's another point.
Assessment developed from the I have to admit the mid-80s already. But this is an example from a study from Gothenburg in Sweden, where they were interested in occupational asthma among bakery workers. And in the end of the 80s, early 90s, there was a huge debate. What was the cause of the occupational asthma among bakeries? That was quite frequent. And we had people who looked primarily at the flour dust, the composition of the flour. And there were also groups that were looking at the alpha amylase that was added to the flour dust to create a more airy bread. And in this study, they looked at alpha amylase exposure. And we know that alpha amylase is a risk factor for respiratory symptoms that are related to allergic symptoms, asthma. And if you look at table 1, what the researchers have done is they have all these alpha amylase allergen levels. They have actually conducted 260 measurements, and 225 measurements were assigned to the category low levels, 22 to the category medium, and 13 measurements were to the category high. And on the first line, you see the arithmetic means, the low category 0.7, the medium 10.7, and the high 46.7. Clearly completely different means for these three exposure categories. And then if you look at the symptoms in this study, you indeed see that the prevalence ratio, the ratio of the prevalence in the low exposed group and the high exposed group, you see a clear trend. Higher exposure, higher prevalence of these symptoms. But now my question is, what kind of improvements would you make to this exposure assessment? So you have indeed a budget to do 260 measurements. And would you go for the same strategy as is depicted here? You have 225 in the low exposure category, 22 in the medium, and 13 in the high. How can we improve this exposure assessment strategy? Susanna.
Yes, thank you. And sorry to come back again but we were developing in Portugal a similar study. So we were able to identify what were the tasks that imply higher exposure to floor dust. And well, those tasks were the ones that we tried to perform more measurements, and we tried to understand what kind of conditions in the workplace that increase this kind of exposure. And of course, in this case, the suggestions is to increase the kind of measurements that can bring some information to the peak exposures. But for that, I think before measurements, I think we have to see again people working and try to understand what they are doing in their workplaces and try to understand how the bread, for instance, is done and so on. So, yeah.
Yeah, makes sense. Daria, you want to add something?
Hello. In Lex, I just wrote about the number of people, so it makes sense. The prevalence ratio is increased in medium and high risk groups, so it would be very important to have approximately the same amount of number of people in all groups to make maybe more strong conclusions.
Yeah, that's excellent observation. But my return question is, of course, why do you think that 225 measurements were actually ending up in the low category? Is it because researchers were stupid? I don't think so. I know these researchers, they are not stupid.
So it's mostly because maybe we could focus on group, don't take into consideration low exposure group. I think mostly, maybe in this case, most of workers were exposed in low level.
Yeah, exactly. But I think one of the problems here was that the knowledge that the researchers had, that we had, was not clear enough, was not, let's say, we didn't know at the start of the study who would be the high exposed worker. And we had problems identifying the activities and tasks that was contributing to exposure. And without that knowledge, we basically said at the start of the study, yeah, let's just do one measurement per worker, and then in the end we will see what happens. So this was an ill-informed decision in a way, and the measurements were done already in, I think these measurements were done in 1991 already. The paper was written much lower, so it was, researchers didn't know. But now you would, of course, immediately say, it's not very strong if you have 13 measurements only in your high exposure group. That's not a very smart decision. But that's sometimes how it goes. You actually think you can predict the exposure because you look at the activities and the tasks and things like that. But it is actually quite difficult sometimes. And this is an illustration that it was quite difficult. And in this study, let's say the classical considerations were asked by the researchers. So they thought about, yes, how many measurements do I need? How can I efficiently allocate these measurements? Do we need to measure all workers individually? Or can we group them together? And then, of course, the next question would be, yeah, if we group them together, what would be the best grouping strategy? And then if we have all this information collected, then we could actually design a good occupational epidemiology study based on our insights into the exposure. So let's say from this introduction, the take-home message is that, yes, we have an enormous amount of choices in occupational exposure assessment strategies. And my experience is that the occupational exposure assessment should be an integral part of the discussion about the study design and the choices you make from an epidemiological point of view. And therefore, what are your assumptions of how exposure is creating a health effect? And I think this is happening much more than in the past, but traditionally 30 years ago, physicians would design the occupational epi study, and then they would ask occupational hygienists to do some measurements to give them an idea about the exposure pattern. And we have moved a long way from there, and now we do an integral discussion in the study design. And the idea of the occupational exposure assessment part in the study design is information on how you can get maximum information on the exposure distribution in your study population. And then if you are interested in that, you need to have information on sources of variance in your exposure, because that will drive your decision on how to allocate your measurements. So let's continue the story. So this bakery study was set up in the early 90s, and and I did a sabbatical in Gothenburg, and I was asked, you know, we have all this data collected. Can you re-evaluate what would have been the best exposure assessment strategy? Because we want to learn from the experience. So let's try to reanalyze the existing data. And that's what I did. And this is just a snapshot of the information we had available. So we had the different jobs, and I'm focusing now on a few jobs only. We had the bread formers, and we had the dough makers. And you see in some workers, we only had one measurement, and in some workers, we had two measurements. And if you look at worker 1, we have one measurement, worker 2, we have two measurements, personal measurements. And then if you look at worker 8, there are actually 4 measurements, and there is a huge difference because some measurements are close to the level of 15 microgram per meter cube inhalable dust, which is actually quite high. So there are a couple of observations here. One is that there are quite some measurements that are in the region of 1, 2, or 3, but there are also some measurements that are higher, and there are even some outliers to extreme values above 12. And then, of course, I started to debate with the original researchers, you know, have you collected information on you know, the workplace. Think of the processes, how it is done, what is the level of automation, is there a confinement in the workspaces or not? How is it with ventilation? How is it with jobs? Do people have fixed jobs or do they rotate when they share activities? How do they actually work? All these kind of questions I asked. And I had the idea, if I have the answer, I can then go back to the data set and try to, for each worker, identify all these critical determinants of exposure. And that would give me a perfect idea about what drives the exposure, so I can do a much better exposure assessment strategy. So this is the kind of first calculation, actually the second table in the article. So you see that the research group, the occupational hygienists actually, they had visited, I think, 15 bakeries, 84 workers. They had conducted 129 measurements. And think about these poor researchers. You know, they had to be at the bakery 5 in the morning. They could do 2 workers per day because the measurement equipment was quite expensive in those days. So this is about a full year of field work. And then you have 129 basically 6-hour average values on 84 workers. And then look at the task groups. So we have 6 task groups: dough makers, bread formers, workers around the oven, confectionery who are making the cakes. Then we have the ones who are packing. And then we had a few workers who were doing anything of the above in a kind of mixed pattern. And then you look at the arithmetic means. It's obvious that the dough makers had the highest exposure. And that was partly due to the fact that they were kneading the dough on these wooden tables, and they would use flour dust to sprinkle on the tables, and they would create their own dust continuously. Then the arithmetic mean was not nicely distributed, not normally distributed. So we calculated also the geometric mean and the geometric standard deviation, and they were quite high distribution, I would say, if you look at the range. So the dough makers, we had one measurement that was 1.2, and we had another measurement that was 16.9. So there is a lot of variation within the same task group. So on average, the dough makers are the highest exposed, but there is a huge variation within dough makers. And then we started to discuss, okay, how should we differentiate these exposure groups? And you know, in the old days, you would simply do t-tests. You have one population, another population, and you compare them with a t-test. And then, yeah, people would argue, yeah, but the exposures are not normally distributed. That was obvious from the figure. So the solution would be, okay, we do a log transformation. And then exposures will become more normally distributed. But then we do the t-test. Yeah, we have multiple comparisons because we are comparing the dough makers with the bread formers, with the oven workers, with the confectionery workers, with the packers. We compare the bread workers with the oven workers, etc. So we have multiple comparisons. Yeah, the solution would be not to rely on P 0.05, but we would ask ourselves, well, how many comparisons do we do? We have stricter P values. Yeah, is that really the solution? I don't think so. And then people started to argue, yes, but this variation, is it really based on a random sample or not? it is probably you go into a particular company and you measure the workers who are there. And it may not be completely random. So the solution would be random sampling. That's difficult to achieve. And then the next question would be, yeah, but you have told me, you know, we have all these different technical considerations. How is it with the ventilation? How is it with the size of the bakery? What is the state of the technology? How will this influence exposure? Well, in the old days, we would say, okay, then we need to do a stratified t-tests where we stratify according to these exposure determinants. And then some people would argue, yes, but then we are losing a lot of power because we are stratifying and we have small samples. So chance will become very important. And then the big debate at the end of the 80s, beginning of the 90s is, yes, we are allocating workers who do the same job in one exposure group. And we call them homogeneous exposed, homogeneous exposure group. But how similar are these workers actually who do the same job? It may differ from day 1 to day 2. It may differ from bakery 1 to bakery 2. So in the end, the solution was don't do t-tests because we have problems. And we need to identify much better how we are going to, from a statistically correct point of view, are going to analyze the exposures. And that's where people move to linear regression analysis. It's basically an extension of the t-tests, and this is the linear regression analysis I did on the data. And you see, if you put in all the data in your linear regression analysis, you can indeed see, well, the dough makers have the highest exposure, the bread formers roughly 50%, and then again 50% are the oven workers, and then again 50% we have the packers. But the problem here is that we had multiple measurements per worker. So the linear regression analysis doesn't take into account the fact that we have repeated measurements within workers. So we need to move on. We need to do another method. And that's where we started to identify the importance of these new measures of variability. So we started to disentangle what is the variation within workers in a particular job compared to variance between workers who are doing different jobs. So we are now trying to disentangle the variance components into within worker variance and between worker variance. And we also want to have information on what is the range in the exposures of individuals. So what is the distribution? And one way to have a clear idea of the distribution of workers who are doing a particular job is to have the distribution and calculate the range of the highest exposed versus the lowest exposed worker. And if you do it more in a formal statistical way, you calculate the 97.5 percentile divided by the 2.5 percentile. So you have the 95% range that gives you an idea about the variability in exposure of workers who do the same job. And then the third, and that was, I think, a very critical measure, is that researchers started to argue, yes, but how is the within worker variance related to the between worker variance? So that's what I started to do in my study in 1994 also. I started to calculate these measures. So now I have the 4 task groups. I have a limited number of measurements. I calculate the geometric standard deviation of the between worker. So here I'm comparing the variance between workers. And you see, yeah, the down makers, the highest versus the lowest exposed worker is an 8.5-fold difference. And that's not much in occupational hygiene. We often see much higher ratios. And then here we also have a very interesting pattern. So what this lambda, this variance ratio here tells us that if you look at the oven workers, the variance within the oven workers is much larger than the variance between the oven workers. So it depends very much on the particular situation, what was driving the exposure. So what we could do now is to pick apart the components of variance. So we had this data set of exposures. We could argue, well, we have jobs, bread formers, dough makers. We calculate the variance that is allocated to the level of the group. And then we move one step further and we try to identify within a group how much is due to the fact that one worker is slightly different from another worker, although they do the same job, but they are slightly different. For example, a dough maker in a large bakery may be actually different than a dough maker in a small bakery. And we also look at within worker variance. What happens if you compare day 1 of a bread former with day 2 of the same bread former? Are these days the same? And you may guess already they are not the same. So that's basically what we did. And based on this variance of analysis, we could play around with how can we assign people to the appropriate groups. And the theory here would be I assign people to the appropriate groups and I want to maximize my between group variance. So here is the actual advice. So if I look at the complete variance and I look at strategy A, I compare dough makers, bread formers, oven workers, and packers. So I have 4 exposure groups based on the activities. And if I use these 4 exposure groups, 61% of the variance in all the measurements I've done is due to the fact that we have dough makers, bread formers, oven workers, and packers. And 22% is at the level of the between worker variance. So dough maker A is slightly different than dough maker B. And then luckily 70% is only the within worker variance if I measure dough maker A on day 1 or on day 2. So this is a clear indication that looking at the jobs that people do is a very efficient strategy to understand variance of exposure. Jobs determine the variance here. But the amazing thing is when you play around a little bit, what happens if we use grouping C strategy? In grouping C, we put the dough makers and the bread formers in one group. We put the oven workers and the packers in one group. And in that strategy, with only 2 groups, we explain more variance at the group level than in the situation with 4 groups. And that was an amazing result because now we could argue, hey, what typically happens is you go to a company, you look at what people are doing, and you think that the activities that people are doing are driving their exposure. from the exposure distribution, we could argue, well, the most optimal grouping strategy probably is grouping strategy C, with only 2 groups instead of 4. So it is not always wise to have too many groups because you think they are important. Try to evaluate whether they really are important based on the exposure assessment strategy. Is this clear for everyone? Do we have questions? Because this is key in understanding exposure assessment. Okay, let's move one layer of complexity now. And so in the early 2000s, people started to argue, well, is it possible to combine the classical linear regression analysis with the traditional analysis of variance? So the previous 2 strategies, so the grouping strategy and the linear regression, can we combine them? And yes, in standard software, it became available around the year 2000. And these models are called linear mixed effects models. And what these models actually allow you to do is they allow you to put in your model, like a linear regression analysis, a determinant of exposure, a large versus a small bakery. That would be a fixed determinant that is not going to change over time, and you can put it in your linear regression analysis. Then the unexplained variance in your linear regression analysis in the linear mixed effects models can now be used to assess the between worker variance and the within worker variance. And it allows you even to evaluate the effect of a fixed determinant on the between worker variance and on the within worker variance. And that's what we did many, many years later. So in the 1994 publication, we had a simple regression analysis. And in 2010, we re-evaluated it with modern insights. And we found roughly exactly the same results in the linear mixed effects model. Why is this in this particular situation not very surprising? That we find almost exactly the same result as the traditional regression analysis that doesn't take into account that we have repeated measurements. But now we take into account repeated measurements. We know the between worker and the within worker variance, but the estimates of the average exposure in the 5 occupational job groups is very similar like in the old traditional regression analysis, which we would consider now as biased. But why were we extremely lucky in this particular example? Anyone an idea? Bendik, you are pointing in the right direction. Can you explain?
Yeah, so it's confirming what you had in your basic data. So if you go to your basic data, you see that what is really predicting exposure is what you're doing at work. So if you're working with forming or creating the dough, you are most exposed. And if you are working with packing or other activities, you're not as exposed. So that's confirmed by your analysis.
Yeah, exactly. So we were quite lucky that the exposure coincided extremely much with the actual jobs. And be assured, in most exposure assessment studies you do, that's not the case. It's and that's because workers do different things at the same time. In modern workplaces, you know, we don't have these strict divisions anymore of bread formers and dough makers, so it becomes a little bit more complicated. So yes, we were lucky. And in essence, we were so lucky that if we looked at other determinants of exposure, like is it a small bakery or a large bakery or a medium bakery? In the old days, we could calculate the average across these bakeries. And we could do some stratified t-testing, but you know already my story, low numbers of measurements available. And if we put this information in a linear mixed effects model, we could explain that the difference between the 3.2 and the 1.14 could be explained completely by the differences in job distribution across bakeries. And that's the advantage of this linear mixed effects model. So if you ever if you're ever responsible for doing the exposure assessment, use linear mixed effects models. That allows you to disentangle determinants of exposure from the random variance that is due to the fact that workers are not exactly identical in jobs, and that there may be variation between day 1 and day 2 and day 3. So my take-home messages before I give you 2 very quick examples that will use these new techniques. So linear mixed effects models are now, I think, the most often used statistical tool, and they can be quite powerful if you use them for fixed determinants of exposure. So all the things we started in the beginning, what are people doing? What is the context, the workplace, the equipment? All that stuff is a fixed effect. You analyze the effect of these determinants of exposure on the exposure distribution between groups, between workers, and within work. And if you are lucky, as in the bakery study, you can now design the perfect occupational epi study. You simply send questionnaires to bakeries. You ask bakers to fill in the questionnaire, and you ask them, what is your main job? And they would say bread former. And if you know that they are probably doing some other activities as well, you ask them, how many % of your working time do you work as bread former? How many % of your working time do you spend as packer, as oven worker? And if you collect that information at individual level and you link it to this exposure model, you will have a very nice cumulative exposure metric for each worker based on their activities and based on your insight how these activities are linked to the exposure. So I will round off with 2 short examples so you get an idea about how you can use these techniques. So this is a debate we had in the Netherlands about a cohort where we needed to have assessment of asbestos exposure over time. And we had one data set available from an asbestos cement company. And interestingly, each 5 years we had some information. We had some information about where the workers were actually in the process part of the asbestos cement factory. We didn't have job titles, but we knew that some of them were more handling the raw asbestos, others were more in the hall where the manufacturing took place. Others were in the hall where they were handling the products, cutting them, transportation, waste management. So we have a limited number of measurements available. We calculate the arithmetic mean, geometric mean, geometric standard deviations. You see quite substantial variation. Over time, there is a reduction in exposure, especially starting 74, 75. There's a huge reduction in exposure. Then the next 5 years, there is again a reduction in exposure. And in the next 5 years, there is a modest reduction in exposure. And we use this linear mixed effects model over the whole data set to calculate the effect of the period and the effect of the job category. And now we can calculate for each of the accrued job categories the estimated exposure for that job category and a particular time period. So now we have a combination of time period and job category in one single model. And that's, of course, a very powerful exposure model. Another example is a study we did. It is a prospective birth cohort study. And we were interested in exposure to bisphenol A during pregnancy. And we had the advantage that we could do some biological samples. So urine samples were collected during different trimesters. And this is the data set we had. So we had 236 women with at least one measurement. So we had urine samples of these women, and we could measure bisphenol A in the urine. And bisphenol A is linked to plastics, and it is regarded as an endocrine disrupting chemical. We had 40 women where we had 2 measurements, 80 women with 3 measurements, and 160 women with 1 measurement. And now the big question is, what would you prefer? Would you prefer to do your analysis on the whole data set? Or would you prefer to do, your analysis on a subset of these women? And this was, a huge debate we had in the research consortium. What would be the best strategy? Does anyone dare to come up with some suggestions? Bendik.
In Norway, we often refer to Winnie the Pooh, saying, "Yes, please, both." I would like the cake, and I would like to eat it too. In Norwegian, it would be ja takk, which would be yes, please.
Yes, you are extremely greedy. You want it all.
I think obviously you will have the best. The 80 women where you could get all of it will give you the best exposure measurements, but you would like to increase your N at the same time. So to me, I mean, as far as it's not too work consuming, I would like to have preliminary data on all subset groups and groups combined. And then I'm wiser. After seeing the preliminary data, my position for making a sound and good decision is better.
Yeah, exactly. So here we are typically stuck So if you were to design this study, you could argue, well, I'd rather have more women with one measurement than a few women with more measurements. That's a basic question. And in this study, I was lucky I could convince the contributor, the funding agency, that it would be nice to try at least collect as many women with 2 or 3 measurements. So what happened? We used this mixed effects model where we had repeated measurements of exposure, but we also had repeated measurements of fetal growth. And that is quite unique in this study because we had fetal growth based on ultrasound, and we could estimate fetal growth during the first trimester, the second trimester, and the third trimester. So typically what happened, this was the paper with the exposure distribution. I'm not going into too much detail, but indeed, if you look at the minimum values, 0.1, 0.2, 0.2, and the maximum values, there is a huge variation. And if there is a huge variation, then one single measurement probably doesn't tell you the true story. So you need probably more measurements to arrive at a better estimate of the average exposure of that particular woman. And that was actually illustrated in the paper where we said, okay, let's mimic the 3 strategies we have. So we use only one sample. So we have over 200 women where we have one urine sample where BPA is measured, and we do an analysis where we categorize BPA in 3 classes, 3 categories, actually 4 categories, or we do it as a continuous variable. And here is fetal weight and fetal head circumference, but I'm focusing on fetal weight. If we do the analysis based on one sample, we see no association whatsoever. It's all statistically insignificant because we have these huge confidence intervals. Then we limit our analysis to those women, 120 women, where we have 2 samples. We again use the same categorization. And interestingly, the estimates go up a little bit. So we see something happening here. And then if we limit ourselves to the 80 women with 3 samples, we indeed find statistically significant associations for the continuous measure of BPA in the analysis and even for the categories. Unfortunately, we couldn't show here that there was a trend across the categories, but this is a clear example that if you have one measurement per woman, and you know that there is a huge variability, then that one measurement doesn't give you a good estimate of the exposure, and thus you don't find any association whatsoever. And if you increase your number of samples, you will, of course, get a better average exposure of each woman, and you start picking up the associations. And that, I think, is a clear illustration of if you go through an epidemiological study and they have only done one sample and they report no associations, then you are stuck with the basic question, no associations found. Does it mean that there is no association? Or does it actually imply that the exposure assessment strategy is so poor that the information you have for each worker, in this case, each pregnant woman, is not reflecting the true exposure? So there will be an attenuation of the exposure response relationship. It will be completely biased. And that's a basic question that you need to ask yourself in every exposure response relationship paper that you read. Okay, my take home messages of this this first lecture is, well, exposure models are very useful to predict trends in exposure across jobs and times. They are also extremely useful to predict determinants of exposure. And if you have that information, you can also evaluate the impact of the variability of exposure on the exposure response association. If the variability of exposure within a person is very high, then any exposure response association will be highly biased. It will be useless to do your epi study. And if you have such a problem with a very large within worker variance, the only solution is increase your number of measurements per worker. And sometimes that is almost impossible. And then we have to come up with a solution in a slightly different way, how to estimate the exposure. Then we can no longer estimate exposure at individual level. We need to estimate exposure at group level, and we are comparing groups and not individuals. So indeed, in the chat, it's interesting. So what is the question here? Is there no association, or is there no evidence for lack of an association? And that's indeed the big question. Here I can argue, well, there certainly seems to be an association between BPA and reduced fetal growth. And in the previous studies that were published in the literature, they could probably not identify that exposure response association because they only had one sample of BPA per women. So the exposure assessment strategy was not good enough to help you identify the exposure response association. So that's basically the take-home message from this example. Any questions? I'm running a little bit out of time, but questions you have? Adam, you have a question?
Thank you. I'd like to ask, I couldn't see your presentations on the website on IS Global. Do you know, maybe Ariadna can explain?
I have sent them into IS Global, so I think they will be published this afternoon.
Okay, thank you.
Yeah, they will be uploaded in the virtual campus.
Yeah, because probably if you go over the slides, it becomes maybe a little bit better understandable why the example of BPA is so interesting. Let me see. Yeah, I was intended to have a 5-minute break in between, but given the time, I